Welcome to this lecture on generalization and search, which is the second lecture of the fourth week of this course in machine learning. For practical reasons, this lecture will divide it up in two videos. So this is part one. The outline of this lecture is as follows. We will first start with some general characterization of the aim of this approach. We will then look on the kind of language and formalism we need in order to work with this framework, and then we will look at the two main categories of strategies for doing this. One, we can say, is generate and test. It's a top-down approach where we generate hypotheses and then search through the instance space in order to iteratively test which hypothesis is optimal. The other category called data-driven strategies for generalization, where we actually start bottom up from the instances. And we will systematically go through all instances, but instead search what we call the hypothesis space that we have built up. And we will look at three ways of searching the hypothesis space: depth first, breadth first, and version space approach. So the purpose of this lecture is to compare various approaches to generalization in terms of a single framework, which we term here generalization as search. Towards this end, we want to cast the generalization problem as a search problem. And alternative methods for generalization are characterized in terms of the search strategies that they employ. This lecture is tightly based on a seminal paper by Tom Mitchell from 1977 called Version Spaces, a candidate elimination approach to rule learning. So, the preconditions for the problem we're going to look at are the following. So we have a language in which to describe instances, which we call the instance language. We have a set of positive and negative training instances of some target generalization that we want to learn. We also have another language we call the hypothesis languages, the purpose of which is to describe our generalizations. And this hypothesis language spans what we call our hypothesis space. The hypothesis space, as we're going to construct it, is a poset, a partially ordered set, organized by a more specific than relation that relates more general concepts to more specific. And then finally we need a kind of matching function or predicate that can test at every point in time whether a given instance and some of our generalizations match. So what we want to determine is generalizations within the provided hypothesis language consistent with the training instances we have, which means that they are consistent if and only if hypothesis matches every positive instance and no negative instance in the data set. This approach is dependent on two constraints. So first of all, it's assumed that the training instances contain no errors, and it's also is constrained by the fact that it's important and necessary that the target generalization can be described in the hypothesis language we have designed. So we can say that this is a theoretical framework because it cannot handle some of these practical problems which are formulated here as constraints. Let's start with saying something about the hypothesis language. So the choice of the hypothesis language has a major influence on the capability efficiency of the learning system. So by choosing a generalization language, you fixate the domain of generalization which a program can describe and therefore learn. So most systems in some way use a generalization language that are biased in the sense that the language is capable of representing only some of the possible sets of describable instances, not all. These biases consist both of strength and a weakness. If the bias is inappropriately chosen, it can prevent the system from inferring the correct generalizations. If it is well chosen, it can guide the induction, so it can actually enable inductive steps beyond the information directly given by the instances. So there is a backside and a good side of this kind of language. Also, the choice of language has a strong influence on the resource requirements. So the complexity of the search in a hypothesis space, if you represent the hypothesis space by graphs, the problem can be exponential, while if you use feature vectors, for example, you can keep the complexity down to linear. Also a language where the ordering you introduce is shallow and branchy, that will typically create a larger hypothesis set. In contrast to where the ordering is narrow, not so branchy in each step, but rather deep. With the approach we have taken, the most important choice to make for our language is which relation to use to relate our hypothesis. So our choice here is a more specific than relation between hypotheses, and the semantics of this relation is given as follows. So if we have two generalization G1 and G2, GA1 is more specific than G2 if and only if the set of instances that G1 matches is a proper subset of the instances that G2 matches, considering all the instances and the matching predicate. So you should note that this definition of the relation is extensional, is based upon the instance sets that the generalization covers. Of course, the definition of the relation is also dependent on the language we have and the matching predicate. So the more specific than relation imposes what is called a partial ordering over the generalizations in the hypothesis space. It provides a powerful basis for organizing the search through the hypothesis space. Finally, one important fact is that in order for the more specific than relation to be practically computable by some program, it must be possible to determine whether G1 is more specific than J1 only by looking at the description of J1 and J2 without computing all the sets of instances that they match. So even if the relation is defined by the instances, it's not tractable to make judgments of the relation between hypotheses by looking at instances. So this requirement that we have to be able to decide on the validity of a relation just based on the description places restrictions on the way our language is formulated. Before we continue, I want to say a few words about partial orderings. In mathematics, a partially ordered set formalizes the ordering of the elements of a set. So a partially ordered set or poset consists of a tet together with a binary relation indicating that ordered pairs of elements in the set such that one of the elements precedes the other in the ordering. The word partial means that only a subset of pairs of elements are directly ordered. As you can see, for example, in the example to the right, where we actually look at subsets of a three-element set x, y, z, you can see obviously that the subset consisting only the element x is not directly ordered with respect to the subset yz as an example, while it's ordered with respect to the subset xy and xz. If every element in the set is ordered, we talk about the total ordering instead. Before we go on, I want to introduce a simple example that I will use for this lecture. So in this example, our instances will be unordered pairs of simple objects, where each object is described by three features. The features are shape, color, and size. And the feature values of shape is square, circle, and triangle. The feature values of color are red, orange, and yellow, and the feature values of size are large and small. Actually, the instance language, if we look at an example there, you can see instance 1 consists of two objects, a large red square and a small yellow circle. So that's an instance. The hypothesis language in this case follows more or less the same syntax. The only thing we do is add a wildcard symbolized by a question mark. And actually the purpose is to function as a generalization for the features values of a specific feature. So it's a possibility here to generalize feature values, but just in one step, using this wildcard. Let's now look at an example. So a small example with just 4 hypotheses structured in a small network. So we have G1, G2, G3. G2 more general than the others. And as you see in the example, ordered from general to specific. So you can see here G is more specific than G2. And you can also see that G3 is more specific than G2. But you can also see that because the way we defined this network through the more specific than relation, G1 and G3 are not comparable generalizations, even though the instances of G3 and G1 intersect. But the sets belonging to these two generalizations do not contain each other. So much about the hypothesis language and its properties. So now let's look at different kinds of generalization strategies. So on one hand, we have the data-driven strategies, and those will be the focus of this lecture. And in that case, the instance space is traversed systematically, and as a consequence, the hypothesis space is then searched. And when we say we use one or the other search strategy, we talk about applying that search strategy onto the hypothesis space. In generating test strategies, essentially we start from the hypothesis space, and by traversing the hypothesis space, we look at the instance space and such that. So it's a general to specific approach. First, a few words about the generate and test strategies. So in generate and test strategies, we generate new hypotheses according to some procedure. And this procedure is typically independent of the data set or the input data. So each generated hypothesis in the hypothesis space is tested against the entire data set available. And for every step, the candidate hypothesis is either identified as an acceptable hypothesis to generalization, or it could be viewed as a node to be expanded further to create new hypotheses, or one can say it's a dead end and prune it away. So generate and test strategies typically considers all data instances in the data set at each step for each new generated hypothesis to be tested. It is also a property of this kind of algorithm is that because for each hypothesis they look at all the instances, not only single instances. They are not so prone to deteriorate it in the presence of noise, because the noise will just be part of the stream of all the instances. On the other hand, it's a problem because if we have a batch learning approach, it's fine, but if you have an incremental situation, it's more of a problem because if new data comes up later in the process, you may have to re-execute the whole generate and test procedure. Also, because of the fact that the generate hypothesis is not influenced at all by the data, the search can be quite expensive. We will now start to discuss a number of data-driven generalization strategies. So actually, many generalization programs employ such strategies that are data-driven, which means that we build up an hypothesis space, and then we revise what we believe to be the current hypothesis or the current hypotheses based on all the incoming data instances. So we will look at three kinds of approaches: depth-first search, breadth-first search, and something called version space approach. And for each of these approaches, we will do four things. We will give some general characterization of the approach. We will sketch a prototypical algorithm. We will trace a simple example and give some comments on that little trace. Let us start with the depth-first strategy. So one of the strategies for generalization, for example, is depth-first. In this strategy, we keep a single generalization, a single hypothesis, as the current best hypothesis. And we call this in this presentation, we call it CBH. So the search starts by choosing, taking the first instances and choose a CBH consistent with that first instance. Then we test systematically the CBH against a new training instance, and we alter the CBH. And we can either alter it so it becomes more restrictive, and this is because if we encounter a negative observation that we do not want to be covered, or we can relax it more because we also have to want to make it cover a new positive observation. However, when we alter it, we also have to look back at all the previous observations to ensure that we do not create an inconsistency with those instances already managed. Also, of course, at every step there are not just a single way of altering the CBH consistent with what we see. There are many options, and we have to choose one. And for all the options there are, we have to try them one by one, and we do that in some order. And if one of the orders later becomes obvious that the choice we have made is not the optimal one, we may have to do some backtracking, going back to that decision point and change and take a second choice. So drawbacks with this is it's very costly at every step to check for consistency with all past training instances. And also, if we happen to make the wrong choice at one of these decision points, to go to backtrack, to reconsider the alternative choices at that decision point. On this slide, you see some pseudocode for the depth-first search strategy procedure. I already outlined for you informally how it works, and essentially the role of the pseudocode is just to formalize this one step further. So what you can see here in the pseudocode, there are actually two parts in the beginning. One part that handles the negative case, and as I already said, when we encountered a new negative instance is in this process of revising the currently best hypothesis, we need to constrain the CBH so that it do not cover that new negative instance. On the other hand, there may be many ways of changing the CBH in that direction, so therefore we have to consider all the earlier instances so we don't get an inconsistency. Similarly, in the positive case, we may normally need to extend the CBH so that it also covers the new instances, to generalize the CBH. But when we do that, we also have many choices, so therefore we also need to reconsider the early instances, so we are not extending it so much that it covers some earlier negative instances. Finally, in the pseudocode, you can see this section where we come into a situation that we discover that we cannot find a suitable revision, which means that the probable situation is that we made a wrong choice at an earlier point among all the alternatives we had. So therefore, we need then to backtrack to an earlier decision point. I mean, backtracking can have many forms. What we talk about here is the simplest form of backtracking, which is chronological backtracking. Now, essentially, we go back to the nearest decision, backward to the nearest decision, and find a new alternative choice there. And of course, that can be recursive because we have many levels of decisions. So, as already said earlier, this can be a pretty costly procedure. So let's look now at an example on how to run the depth-first search and a trace for that example. So in this example, we have 3 instances. First, we have 2 instances which are positive, and then we have 1 negative instance. And what you see on this slide is the current best hypothesis in 3 versions representing 3 steps of the depth-first search generalization algorithm. So some comments on this example. So the first positive training example leads to the analyzation of the current best hypothesis to CBH1, which matches no instances other than the first positive instances. When the second positive instance is observed, CBH1 must be revised in order to match the new positive instance. And you should notice here, of course, there are many plausible revisions to CBH1 in addition to CBH2. What is not visible here is, of course, the order of these alternatives. But the system picks what is considered the first alternative. So now we got the CBH2. So after these two positive examples comes a third training instance, which is negative. And being negative, it conflicts with CBH2. In this case, although CBH2 could be specialized to exclude the new negative instance, no such revision is considered with the earlier observed positive instance that we already looked at. Also, one observation we should have here in order to understand the example is that every instance is an unordered pair of objects, so it doesn't matter in which order the two objects are placed within the instance. But actually now, considering the third negative instance, the system must then backtrack to an earlier version of this current best hypothesis, reconsidering its previous revisions to determine a CBH3 that is consistent with the new negative instance as well as observed positive instance. So this is the result in the end. For practical reasons, not to make this video too long, we make a break here and continue the treatment of the other algorithms in the part 2 video. Thank you. Bye.